is, the difference between the average value and the actual values mean squared, and we'll see that in a second. But so you get regression trees, and they work the exact same way. Everything Neil said is true. The only thing is, your measure of impurity becomes, means, variance or mean square error, and you can do the exact same thing. And having said that, I want to share my screen. And which one do I want to do? I think it's this one. I think this is it. I think I just need to, yeah. So it's called a bagging example. I just like that. So we're going to go back and look at the Boston housing data set. And next week, I'll go through a full-blown example. I'm not going to use the Boston data set, but I'm going to go through a full-blown example of using Caret. In some sense, this is a bit of Caret light. Okay, so one question you can ask is, so in R, there's various packages for trees, and there's one called tree, which is the one I'm using. And I don't know if that's the best one anymore. I think some people say R part is better, but as Neil said, trees are the basis for some more sophisticated packages where you look at random forests or you look at boosting of various sorts. And these outperform trees almost always. And the reason is because the models that trees produce tend to have higher variance. And one thing people liked about trees is you have this splitting. You can sort of say, I understand what's going on. I'm going to take this, and if this happens, I'm going to do this. And it's very easy to understand. But with really big and complicated data sets, the splitting just becomes so complicated and so many splits, it's not really intelligible. Incidentally, another piece of history, trees were invented by Breiman. He was asked to solve a specific problem. A hospital said they had data of patients who had heart attacks, and the question was asked, how can we decide which patients are at the greatest risk to have follow-up heart attacks? And they had some data of patients who had heart attacks, and they used that to produce the tree of decision based on various factors like age, systolic blood pressure after the event, and a few other things. And they came up with a decision tree that was actually used in the hospitals to decide who were the patients who were most in need of follow-up care. Okay, so we just want to see, I want to show you, and this is R, of course, not Python, but it's very similar, how...
you can also see if you can survive the Titanic disaster, right?
Okay, so the Titanic disaster is the quintessential Kaggle demo program. And I think you can use trees, but I think random forests and boosting work much better for that too.
This would classify us all as being dead, right? All of us here at the...
I think most classifications say that you and I, Niels, do not make it. But the one thing we have going for themselves is the reason why the elder white men didn't live was because they were gentlemen and they gave up their spots on the boat to women. I won't speak for you, but
I think the first question,
you have to be special.
The first question in the tree is, are you a man or a woman?
Right.
If you're a man, you end up pure dead. That's
very few men survive, yeah.
Yeah, right.
Okay, so I'm just going to, this is just showing you loading the packages. And it's going to use random forest, which is a good package for random forest. And whatnot. Okay. So remember, let's just go about it. The Boston data set is information about various zones in Boston. And the predicted variable you want to track is medieval, or, well, some people say it's medieval, but I think it's median value. It's the median value of a house in the zone. And you have all these different factors. And you have the crime per capita. The zone is proportion of residential lot zone for lots over 25,000. There's a dummy variable for all you near the Charles River. And you can see, just, I don't want to waste our time by going over these. If you're curious, This file has been uploaded and you can read them. But it's a bunch of different numbers that, relate to how you might value a property. So we have that, and we want to predict the median value of houses. So you may recall regression worked pretty well, but not great. Let's see if these things are better. So the first thing I do is I'm just going to divide it into a test train, and I almost always, if I have no reason not to, use 70% for training, 30% for test. So I did that. So if you're doing it in R, there's, I'm always happy to point out problems with Python, but I think it's fair to point out the problems in R too. So R has one huge syntactical issue associated with linear model syntax, and that is so the command to create a tree is called tree, and you use the same syntax of I want to compare median value. The tilde dot means to all the other variables. My data set is Boston, and I'm going to use a subset called training. And if you do that, you'll get an error message. And if you're very familiar with R, this says that the error message is a big hint of what's going on. It's looking for some sort of list, and you haven't given it a list. You've given it a matrix of data things. And this is typical for LM, but not so much but it doesn't happen in Caret. The function it's what it really wants is an index when it says subset. It wants the index of the subset. It doesn't want it. So that's the problem. And it's easy to solve. I don't like to give it an index in case I want to do other things with the training set or the whatnot. So the solution I have is I use the tree function. I want to compute median values to all the other variables, and I'm just going to give it the data set that's the training set. And then I'm just call that tree.Boston. And my predictions, I just predict now works just fine. I want to predict with my model is called tree.Boston, and my new data is the test data. And I can plot that, and you can see that it's not perfect, but it's predicting roughly an equal number above and below. So it is doing that, and Niels mentioned the mean square error.
Adam, the one where you got the error versus this one, what's different? Like I see you still have tree and you still have train. What's different between this?
The difference is, okay, so if you go back, I said compute tree with the same formula. I said use the data Boston and just use a subset of train data.
Okay.
So this is saying you create a tree for the median value against all the other variables using the Boston data, but take the subset that's trained. Whereas the more direct thing is to just say, I want to create a tree. I want to predict the median value against all the other variables. And my data set is the data set I call train.
Okay.
Okay. And then the predict function then works nicely. I created this object called tree.Boston. And I just say, all right, predict with the new data, which is the test data. And then I just plotted it over here. You can see it's working pretty well in the sense it's an equal number above and below. And then I computed the mean square error. So the tree in the end gave an error of it was off about $5,000. Right. Remember that the median value was in thousands of dollars. If it was really off by just $5, wow. Okay, so I said it did better than regression, but it's 2 lines of code. Let's just do it. I mean, I can do the linear model. LM is the command for linear model, and it's the same thing. My formula is I want to compare median value. I want to predict median value with all the other variables. I give it the trained data set. I create this linear model. I throw it in the predict function. The new data is the test. And I want to see how that compares. And I see it's slightly worse. About 5% worse. So there is improvement to doing the tree over the linear model. So I think at the time we did that, people thought the linear model was pretty good, but we see an improvement. Okay, so I'm going to compare the linear model and the tree, and we're going to do random forest and boost. As Neil said, bagging is when you look at subsets of the data. So you just take sample with a replacement. So the key to that is to take a sufficiently large number of samples. If you resample once, you could, as Manish pointed out, been incredibly unlucky and just pick the sample that was one data point repeated however many times you originally had, and that's going to give you a really crappy model. But if you do enough trees, you're guaranteed that these things will average out. And so the point about doing bagging is it will reduce the variance. As I said, trees tend to be high variance, and bagging is a procedure that will reduce variance. So I want to, for various kinds of models, I have the predict, my predictions. I'm just going to compare that to the MSE and do this. So I'm going to create a matrix to do that. So I'm going to pre-populate it with zeros. I'm going to have 6 rows because I'm going to, in the end, do 6 models. I'm going to have 3 columns of data because I'm going to have, as you can see here, the mean of the test value. So what's the average value of the houses in the test? What's the average value of the prediction? And what's the mean square error of the thing? So, predict comp, I'm just calling that the name of the matrix. It's of zeros with 6 rows and 3 columns. And I'm giving it the row names of what they are. I'm going to compare the tree, bagging with 250 resampling, bagging with 500, random forest with 250 samples, trees done, and random forest with 500, and finally boosting. And I'll talk more, I'll add to Neil's discussion when we get there. And I'm just going to, as I said, just look at the mean of the test housing values, the mean of the predicted values, and we look at the mean square error. And, well, the first column we know, it's just going to be the mean of the test for everyone. So I can make the first column just be, I just want it to be that same value. So I want to round it to do decimal places for neatness. So I'm going to make a matrix with the mean values, and I'm just going to have 6 rows 1. And you can see there it is. I've pre-populated the mean of the test is. I'm going to have to add in these other values a few times. So let's write a function to do it. So I'm going to have 2 things. I have the test values for the median housing, and I'm going to have my predicted values y hat. So I want to create a matrix that'll give me 1 row. So I'm going to make a matrix of zeros, 1 row, 3 columns, 1, 2, 3 columns. I'm just going to run on all these different things. And the first one, I didn't need this duplicative, it's just the mean of the test set. Then I'm going to take the mean of the prediction. And finally, I'm going to compute the mean square error, which is the square root of the average of the difference between your prediction and your actual quantity squared. And return out, by putting that last line, I didn't actually need return. That just means if I run it, I'll actually see the value. Okay? Are there any questions on any of this?
Matrix 0, 1, 3. So 1 row and 3 columns. What is the first component 0 in that matrix?
No, that means it's all zeros. So if
all zeros. Okay.
Yeah. So you have to give you 3 pieces of information to create a matrix.
Yeah.
What the values are.
Yeah.
Right. How many rows and how many columns. I mean, it doesn't have to be constant. For example, I could just say, so the rnorm function gives you random normal values. I could have had rnorm 3, and it just would populate it with 3 random values. It's good to when you're pre-populating, when you're instantiating a matrix like this, it's good to pick a value that's easy to see and is unlikely to occur in real life, so you can see if you have a problem.
Yeah.
So when I'm done, if I see a bunch of zeros over, right now I see zeros, but if when I'm done I see zeros over here in these 2 columns, I know there's been a problem. All right. Okay, so this didn't correct. It should be what is out of 3. And the question is, why isn't out of 3 just y hat minus test? I will show you that. Where is it? Okay, out of 3 was the square root of the mean of y hat minus the test, the prediction versus the actual value. You add those, subtract them, square them, take the average, and then take square root. And the question is, why am I squaring and taking square root? And, there's too few people here to formally do tests, but so people should just shout out what they think. And the answer, my three choices, that will work too. Second answer is that's just a different way of looking at three things in three. And I think I know which one Neil is going to go for. This is just the standard error. So
why am I taking squaring and taking square root? If we don't square, then it will be plus and minus. It will go to 0, right? So
absolutely, that's why you square them, and then you take the square root because you want to have the same units as you originally had. Yeah. So this is just standard L2 error. Okay, so oops. So recall, as Neil said, that bagging is where you take the data set and you sample with replacement, and you use that to train your model. So if you did it just once, it can be very screwy. In particular, as I recall off the top of my head, I think it's 63. On average, you only use 63% of the data. There's only 63% of the data points are distinct in any given bagging sample. That's the expected value, to have 63% distinct. So you need to do it a bunch of times. And I'm going to use the random forest function because what random forest does is it not only randomly selects the data points, but at every split, rather than considering all the possible criteria, it only uses a specific subset of, a specified number of subsets. So in other words, it randomly chooses the data, and at every split, it randomly says, rather than splitting on all the possible variables, I'm going to pick a random subset of those. So if you do random forest, but you say, I'm going to look, the number of variables to use for the split at every time is all of them, you've recreated bagging. Is that clear?
no, sorry, could you repeat once again?
Yeah. So random forest adds another. So if we didn't have this mtry, okay, and we'll talk about importance in a second, this would just be bagging. It would just say, compute the median value against all the other variables. My data is try, and it's just going to bag the data set. What random forest does is it says, at any given split, you pick a specific number. So let's say there were 100 variables, mtry 13, you say, randomly pick 13 of the variables and only use one of those 13 for the split. Remember, all these things are looking at all the possible places you could split with all the possible variables to find the one that gives you the maximum reduction. Okay? So when you use random forest, it says don't use all of them, just use a subset. So in fact, if you had a photographic memory, or take my word for it, there are 13 independent variables. So when I say mtry equals 13, I am saying use all the variables at every split. So I'm not doing a real random forest, I'm just bagging. Okay? So this is the formula, and importance equals true. Well, first of all, n-tree equals 250 means I'm going to do it 250 times. I'm going to sample my data set 250 times, compute 250 trees, right? Now remember, each time, in fact, it's looking at all the variables, and at every split is picking the one that gives the maximum decrease, not of entropy or a Gini index, but the maximum decrease in the mean square error in the nodes, okay? So one thing you could do is you could keep track of it. You could keep track of, at every node, on every tree, what variable you used and how much, in fact, did it reduce the mean square error. So it takes a node and it divides it into two nodes. And the one thing you know for sure is that the weighted average of the mean square error of those two nodes is lower than the node above. So you can say, well, what variable did it split, right? And what's the difference between the weighted average of these two mean square errors compared to the mean square error of above? And you can keep track of that. And obviously, if you're picking at any given node, you're picking the one that does the maximum, but you keep track of, does some variables lead to really large reductions in mean square errors, whereas others don't lead to such significant differences. So this importance equals true says keep track of that. Okay. So then, but I do run it. I create this model, which is 250 different trees, and then I can run predict on it. And my new data test as before. And then I remember the comp out function simply just tells me, in essence, it's computing the mean square error between my prediction y hat and my actual value, which is test.mdv. And now I can put this in the second row. And now, lo and behold, I mean, obviously, I don't know, that's weird. I must have done something. Oh, I forgot to write round in it. So this is not showing the same because 22.50658, when you round it to 2 decimal places, which I forgot to do, it can be 22.51. Okay, but you can see the predictions are well, a little closer, but more importantly, the mean square error is going down. Okay, so it's a reasonably significant difference from $5,000 to $4,000 by using bagging as opposed to using a tree. And this is the variance averaging. This is exactly where you're seeing the variance averaging come into play. You know, you might have gotten lucky with one tree or not lucky, and of course we didn't do all the details. Trees should be pruned, but by averaging over 250, we improve. So I said the variable importance tells you how much it did. So let's see. So this shows you for each of the variables the percentage increase in MSE or decrease that you got from these variables. So looking at these, you can see very clearly that the most important predictor in the random forest was the number of rooms. It had the, it gave a, 45% of, if I'm reading this correctly, well, essentially 46% of the decrease in MSE you saw over all the models came from rooms. Unimportant variable? Well, there's two things I think that are interesting. Well, first of all, it says Charlotte being near the river wasn't important. The next least important one was the zoning, whether it was industrial. Tax was somewhat important. I forget what DIS is. Let's go back and find out. Weighted mean distance to the 5 Boston employment centers. So that makes sense. You're close to work. That made housing more variable. And I don't remember LS stat either, but you get the idea. But even nicer, you can now get charts of this thing. And
what was the second column? Like node purity? What is this one?
Sorry?
What's the second column? Node purity?
Node purity is just a different measure of well, honestly, I just use MSE. Okay. I don't remember. I could look it up. But increased node purity, it's some other numerical measure of by what percentage, how much you got to nodes with just the same value by using those particular variables.
Okay.
I don't remember, honestly, I use MSE myself. I forget what increased node purity means. I can look it up if you're curious.
Yeah, I think there is some difference between the two definitions of weights computing because 11% P ratio translates to 447 and 8% crime translates to 808. So it's not like one.
No, they're not exactly the same. You can see this is about 100 times larger, and this is 15 times larger. This is 6 to 140 is 25 times larger. So they're not the same.
So Professor, this increase in MSE is across all the 250 trees would be.
This is measuring over all the trees.
Yes.
The point is and that's the important. That's very important that it doesn't just pick which tree it thinks is best. it looks at all of them to get some sort of average. In some sense, by going, it's reporting a gross amount of reduction, but since you're going over so many trees, you don't fall victim to overtraining on one particular data set. Because these trees, look, in this set, as I recall, there were 700 different zones. So once you get to 700 nodes, you can always split it so each node has just the one value, and then you're perfect, right? But if you use that tree, you're going to do perfect on your training data, but you way overfitted, and it's incredibly reasonable to expect that when you go give it new data, you're going to see very bad results. So when you train on 250 different data sets, if you will, it gives you a chance to, to see different sets of circumstances and reduces overtraining, which is to say it reduces variance in the predictions. But this is a nice feature, and Niels, I'm sure, is going to give you exact definitions next week, but this variable importance is one of the really nice features that you can see once you do ensemble models like bagging. Okay. Any other questions? Okay, next slide. Okay, we're going to repeat this now with 500 iterations. We're going to, sample the data set 500 times, and the question is, do you think this is going to improve things? And the three choices are yes, no, and maybe.
Yes.
Tejas, do you want to guess?
Yes, it should be yes.
Niels?
Maybe.
I'm with you, Niels, maybe. It probably will, but you do have the issue that you could run into overfitting. First of all, you could be unlucky, but but the other thing is now 500 isn't nearly enough. But if you took 10,000, you would definitely overfit, and then you probably wouldn't increase things. But I'm going to go maybe, or usually. But as I say,
It's always the safest. Maybe is always the safest choice.
Maybe you're right on that. I don't know. But let's do it. And when we do it, we see that the BAG RF, it improves the mean square error, but very, very slightly. Okay. So the only difference between the two formulas is I've gone, oh, wait, I didn't say how many times to do it. And that's because it turns out that for this model, it defaults to 500. So if you don't tell it, it just automatically gives you 500 trees. So let's move on. So random forest, the difference is we're not going to have m try equals 13. Okay. Now you can, if you were in a situation where you're using caret and you really weren't sure, you could, make this one of the variables that you wanted to tune on. You can make this one of the hyperparameters. And you could say, try, 2, 5, 7, 10, and 13, or whatever you want. But the random forest, there are sort of empirical defaults for what you should do based on whether you're doing a regression trees or categorical trees. And if you don't tell it, it will pick for you. So I'm just going to do this. So I'm going to not tell it. So I'm going to let it, and I think it's P over 3. So it'll take 4 or 5 trees at every split. And I'm just going to run the random forest function, which is the same function, same formula. The only thing is I'm not forcing it to use all the trees. And so I'm going to, everything works just the same, predict, and then I use my function to compute MSE and populate the other 2 elements of the row. And then finally, I do the same thing for 500 trees. And we can see that once we go to random forest, we improve again. But when we go to 500, maybe we are hitting overfitting, or maybe it's a statistical aberration. But it's better, but this is claiming that the 500 doesn't actually improve. And the one thing I was kind of curious to see was, did when you did the bagging versus when you did the random forest, did it change what variables were important? So here I had the importance of the 500 bags and the importance of the 500, and I just compare them. I'll push this down here. We can see, and let's just look at MSC, and we see again that rooms, the number of rooms is the most important one. It's 55%. But when we go to the random forest, it's still the most important one, but it becomes less important. It goes down to 33%, which suggests that, maybe the reason why the model is doing better with the random forest is because it's relying less on the number of rooms and more on other factors to determine what it does. So, what's gone up?
The industrial area.
Yeah, industry has gone up.
Crime, industry, yeah.
Crime a little bit. Yeah. So it's, kind of interesting to, to compare them. And finally, Niels, we haven't really talked about this, but boosting is a very interesting method that usually involves trees, and that's why it's always good to understand them, even if you're not going to create tree models. But I did do just one simple model, and to give you an idea how long ago it was that I did this, I used the gradient GBM function, which means I used the GBM package. The GBM package has since been orphaned, which means the developer has said, I'm not going to work with it anymore. If there's any problems, I don't care. Leave me alone. I have no interest in what happens to it anymore. And the reason why is because people using, ideas from gradient descent, and in fact, actually the Newton method, and I'm to bet money that you're going to hear lots of interesting details about this next week from Niels. They discovered that you could use the Newton method very effectively when you were doing boosting, and you could much more rapidly produce results than you would with gradient descent. And so traditional packages like GBM, which used gradient descent to compute things, went by the wayside because XGBoost using Newton method appropriately were just much faster. But in any event,
Light GBM, right?
Sorry?
Light GBM.
Light GBM. Yeah, Niels likes light GBM. I'm old-fashioned. I'm still an XGBoost guy. But you mainly claim that light GBM is much easier to install in Python, right?
Yeah.
Yeah, for our both packages are very easy to install. There's no problem installing either.
Well, it's for, if we want to use GPUs, it's XGBoost is a little harder to install.
Yeah, I did actually, read something, about a guy did some very extensive testing, and it really depends on what kind of, if you have lots of CPUs, certain programs are better. If you're using multi-nodes, others are. So it's very interesting, that there's no such thing as the best boosting package. It depends very much on your hardware. But these are all orders of magnitude, literally orders of magnitude faster than gradient boosting. But in any event, it does use the same formula. I'm going to compute median value versus train. And that's just telling it I want regular numbers. I'm going to, yeah, this would take a while if I ran this, but I did run it, and I get, this is, you get a much nicer variable importance chart. But it does still say that room is the most important one, the number of rooms. Okay. I did, then I did a test on a bunch of them, and I, yeah. For some reason, I don't seem to have computed the MSE of the gradient boosting, but maybe I can do that very quickly. It does improve. Hold on a second. That's not what I want. Okay. Oh, no, I can't. Oh, hold on. I'm just going to tell you in a second what it was. Okay. So when I just did that very simple one, actually the median square error went up significantly. How do I resume? Okay, resume share. So I don't have it here, but it actually was worse because I didn't very intelligently choose the hyperparameters. But I promise you that if you do choose them properly, you will get them down. I think I want to say that I got down to 2.8 or 3, so about under $3,000 for the mean square error when I properly tuned the boosting.
One question here.
Yeah.
In bagging, as you increase the number of trees, you're saying that you have more chances of you will be increasing overfitting. Is it because every time you create a new tree, but still it will look at the majority and decide the
It's an average. You would have to take way more trees than 500 to get overfitting.
right? But I'm just wondering, like, if let's say if you have 2,000 trees or 10,000 trees, why would that create an overfitting scenario?
I think in this case, no, but if you took like 50,000 trees, I think you would probably get into the realm of overfitting. I mean, you could do,
No, I'm just trying to understand, like, theoretically, like, by increasing the number of trees, why the chances of overfitting is becoming bigger?
okay, so the way we created these trees, any given tree will certainly overfit, right? When you create an average of the trees, you're decreasing the average fitting because you're decreasing variance.
Right.
These are, I mean, by bagging the data set, you're creating, you know, if not completely independent variables, but, you know, reasonably uncorrelated variables, right? So at some point you run into the issue of the variables are no longer uncorrelated. At that point, I mean, imagine if you created enough models, so essentially you got so there was excellent chances that you were getting data sets, some data sets with just a few examples. At that point, you would probably start running into overfitting. I mean, but I do it, you know, I mean, it was from 250 to 500 or even 5,000 or 10,000. You know, it would be very, very bad luck if you overfit. And you can overcome this bad luck very simply by just rerunning the whole process of producing 10,000 trees, you know, a few times. So for example, you know, it takes almost no time to run 5,000 trees. And in R anyway, in our studio, any session uses one core. So if you wanted to, you could always just sort of, you know, let's say you had a double core machine and, you know, so you have 2 threads per core, you could run up 4 instances of our studio and do 4 of them and then be almost guaranteed. And, you know, actually you don't even have to run up 4 instances. There's, you know, par 4 loops and various other ways of, you know, parallelizing things in R. So. But yeah, no, I mean, to vote, I mean, it was a bit, it's not facetious, but it's really just 500 trees is vaguely beginning to be enough trees to create problems. You're right about that. Just, as Neil said, maybe is always safer.
Well, you can see it. I mean, in random forest, if you take a very large forest and you look at the decision boundary, you get something very jagged, which is an indication that you're overfitting, right? So you get a lot of little leaps and cuts in the decision boundary.
Yeah, I'm having trouble hearing you, Niels, but I assume what you're saying is, I heard the part about jagged boundaries. And jagged boundaries, as I'm sure you were trying to say, always means overfitting.
Yeah, often. All right. Yeah. But that's what you can see. I mean, you can if you experiment and try to take very large bagging, a very large random forest, you'll see that you get very jagged decision boundaries, and is definitely an indication of overfitting.
Yeah, great point. All right. I think I just did one more thing where I took a look at a large selection of I must have just run the code. I seem to have, instead of see. Oh, I see what I did. When I wrote the code, I forgot to take square root. So hold on a half a second. I mean, so, oops. So these numbers are the squares of what you want. Where is that? It's over here. So, hold on. 21, 2, 3, square root. Yeah, so, what did I have? Yeah, I don't know. I'm the only thing I can read from this that I believe is that all these models relatively independent from 1,000 to 6,000 trees. They gave you about the same error.
This question is for MSE calculation. Won't you need y hat minus test $mdev MEDV? Why it's just y hat minus test?
That's why it's giving you these weird numbers. It should be test $MD $ median value.
Yeah.
That's why it's giving you these weird values. It's what we call a typo. I think that's the technical term for it. But if you change this test to test dollar, oops, it would give you the right thing. If you want to wait a half a second, I can't share. Well, hold on a second. Let's see. Yeah. Okay. So what I'm going to do is stop the share and give you a different share. Share. Where is it? I think it's this. Yeah. Yeah. So if I go in here and change this to test $MEDV, now it'll take
Square root.
a little bit of time to run this because I'm running it over.
And you also need to take square root of that.
You know. SQ root. Okay. I think those are the two only errors I could make, and I did make them. I think this takes like a minute or two to run. Obviously, what takes time is when you get 4, 5, and 6,000, trees, and I'm
So one may ask, like, if boosting is predicting better, and we see that tree-based methods
typically
are doing
produce
better
best.
than
Yeah.
regression. So why one would do linear regression, and why? I mean, what is more important to understand here is that between these methods, what method will work better in a given scenario? What is a scenario where you may want to use just linear regression versus when you want to use probably tree-based method? I mean, I understand lasso and ridge because they avoid overfitting, right?
Yeah.
But when it comes to comparison between lasso, ridge versus tree-based method, which one will one pick?
Let me make sure I understand your question. Your question is, I understand the point of using ridge and lasso is it will reduce overfitting. Why use these models?
No. I'm saying that these models looks very effective, but the question is, would it make the other models useless? Because if these models are reducing MSE by such a big margin, then people will always use these models, and they will not use lasso and ridge.
I see. Yeah. So why use lasso, ridge, or even linear modeling when you have these things?
Correct.
So there's, to me, I answer that, and I'm curious to hear what Niels has to say. But my answer is two parts. The first part is for many things they are used. Like, for example, in the Kaggle competitions, and in most serious machine learning problems where people are producing models, they're not using regression anymore.
Yeah.
But why would you ever use regression? You could see how much longer it took to run this than it did to run, just even the basic tree model, let alone a linear regression. So there are times when speed is an issue.
Okay.
And so if a linear model is fast enough, is reasonable and much faster, there may be times you prefer. Along the same lines, you run into issues of explainability. People love linear models because they understand them.
Okay.
Now this information is 5 years old, and maybe it's changed. But I knew a guy who worked for a consultancy, and they did work for insurance companies and hospitals and whatnot. And these hospitals would let them use logistic regression, would occasionally let them use trees, but wouldn't use any more complicated models because they weren't happy with them because they couldn't understand what was going on.
Yeah.
And for example, in credit scoring, banks, for example, it's the law. They can't just say, we ran a model, you're a bad risk. You have to be able to explain it. So there was a long period of time where banks were using logistic regressions, and because they knew these other models were better and would give better predictions, but they weren't allowed to use them because they didn't know how to legally justify them.
Yeah, but then still,
But you know what? All right. So you're in finance, and I presume you guys do a lot of regression. One thing the problem with these models, I think, in finance, is they're not going to work for high frequency. They're too slow. But maybe guys have figured out how to make them faster and are using some of them. I don't know. But when and the problems that I've solved, I think almost always, if time wasn't an issue, gradient boosting provided the best solutions.
Okay, it looks pretty good, 3.6.
You can see the wide range as you go from, not a lot of iterations, and not a lot of models, not a lot of depth, and not a lot of trees, down to a lot of trees and a lot of depth in the model.
But is it true that these methods would always provide better results than logistic regression, or?
Usually, suppose your data is actually linear. This isn't going to be any better.
Right.
Yeah, I think one of the reasons also is that people know how to do statistics on linear regression. and it's not so easy to estimate risks and uncertainty in these other models. I mean, you don't have it's sort of like for linear regression, you have well-developed methods and distribution of the coefficients and stuff.
Yeah, you saw that, you know, granted, I'm not running a state-of-the-art, but this is a decent computer. It's an i7 chip. Now imagine trying to run this model 10,000 times. It took a minute or two to get decent bootstrapping confidence intervals.
No, for
So
sure.
that's a good point.
You can definitely get empirical distributions out of running it many times, but
Right, yeah.
linear regression has been around for a long time, and it's sort of very well. The statistics is very well understood, and that has a lot to do with tradition, right? If you're a drug company and you're gonna have to submit something to the FDA, then it has to be in. You can't use machine learning or prediction there. That's not going to work. So they're not going to let you do that. So, I mean,
But I did know some people who are actually in the, you know, not payday loan, but, you know, the online loan business. You know, we'll give you an answer in a minute. And all you're doing is you're getting, you know, just minimum amount of statistics from a credit agency and computing your credit score. And they were all using random forests.
Yeah.
And they were eating the bank's lunches because they were that much better. They could offer still very shitty, but much better, really shitty rates than the banks on credit cards. No offense.
Yeah, no, I think that's true. I mean, on the sort of consumer side is fine, but if you have to submit things to a federal agency to get approval and stuff, then you're going to have to do some kind of statistical analysis that they can understand, and it's an accepted way of doing it.
Right. You can go to a bank and say, we ran a logistic regression and we decided there was only a 20% chance you're going to repay.
Yeah.
But, you know, they were happy with that. But if you said, hey, we did a gradient boosting model, and the gradient boosting, we said you had a 20% chance, they said, what's gradient boosting?
Yeah, exactly.
And then a few hours later, they said, oh, no. That's no way.
On your I mean, if you look at your phones and stuff, it's all using machine learning and gradient boosting and deep learning and stuff. So all this stuff that's going on your phone is.
Okay.
Right.
Yeah.
Yeah, I think great session. Thanks, Adam. Excellent. I think
And next week, I promise a functional, full-blown carrot demonstration.
All right. Thank you very much.
Okay.
Thanks a lot, professors. Thank you.
So, Neil, we can talk about it, about that person on an email. Okay. I also need to send you an email and Adam about something else I thought about. So I'll send you.
Okay. All right.
All right.
Sure. Sounds good.
Thank you.
Thanks.
All right.
Bye-bye.
Niels, I will see you next week, and next week I will see you.
And on Thursday, for sure.
Thursday for sure, and hopefully Wednesday. I'm gonna.
All right. Sounds good.
All right.
Okay.